Okay guys, so up to this point we have talked about limits, we've talked about derivatives, and then we did a little bit on related rates where we applied those derivatives. So today is going to be another extension of applications of the derivative. So this is our first step into what we call function relationships, where we look at how the derivative and how other parts of our function all kind of come together and essentially form a relationship. So what I want you to do is just look at this function for a minute and think about all the things that you recognize. Think about things that you've seen back in Algebra 1, Algebra 2. Now, granted, I understand that this wouldn't be a function you would actually see in either of those classes for the most part, but there are pieces of this graph that you learned in those early classes. So what I would recommend that you do is pause the video, write some stuff down, and then I would replay it and then see if some of the stuff that you come up with is similar to what we have. So again, push pause, come back. Some of the things that I recognize thinking back on what we've done in the past is the fact that this part of our function right here is very linear, okay? But then the rest of this graph looks like a polynomial. So this is what we would call a piecewise function. Because it comes in two separate pieces. It's got a piece that's linear and then a piece that's more of a polynomial. Overall, I would also say that this function is continuous from negative to positive infinity because there are arrows indicating on both sides that it's going to negative and positive infinity, but then also there is not a place anywhere along this curve. If I drew the curve or drew the function, I would have to pick up my pencil. So that's going to tell me that it's continuous. Now, another question, thinking back to what we've talked about in the last couple units, is this function differentiable? What do you think? Parts of it are, but overall, there's one little spot right here that makes it not differentiable. I'm going to change the colors real quick. This right here is what we call a cusp. It's a sharp turn in the middle of our graph. It's actually because we have a linear piece connected to a polynomial piece. So these two things come together. Because it's a sharp turn, this is not differentiable here. Okay. However, the function is differentiable everywhere else because you have a linear piece right here and the rest is all a nice smooth curve. So if you were taking the derivative at any one part of the graph, you could find the derivative anywhere except for this piece right here. Okay. So if we wanted to differentiable except at cusp. Okay. I think I spelled that right. That does not look like it. Let's fix that at cusp. There we go. Let's see, what else do we know about this graph? Well, it has even end behavior. Why would we say even end behavior? Not an even function. There's a difference between an even and an odd function. Even and odd functions is going back to symmetry. This doesn't have any form of symmetry, but it does have even end behavior because the end behavior goes the same direction on both the left and the right. It goes to negative infinity on this side and to negative infinity on this side. So your end behavior is negative infinity and negative infinity. Okay. Most of this stuff is more recent things you guys have learned about. Another thing we talked about a lot in Algebra 1, what do we call these things? Right here. Anybody remember? Okay, those are your x-intercepts or your solutions, your roots. So there are 5 solutions to this function, and technically one of them is a double root. So you've got 1, 2, 3, 4, 5, 6. So actually I could say there are 6 solutions. Well, I guess I should say 5 unique numbers, but one of them is a double root. So let's do this. We'll stick with 5 solutions. Okay, but because we have a bounce right here, we'll say that 1 is a double root. Okay, that goes back to multiplicity and the things we talked about in pre-cal last year. Okay, is there anything else that we can think of? Oh, so one thing I guess we could say, because it's differentiable everywhere except at the cusp, we could say if this function, if I were to identify this as f of x, I could say that f prime of x does not exist at x equals, what's my -5? Okay, we could get a little bit more specific with that. Trying to think if there's anything else. We can't really identify where those solutions are because they're in between and we don't know enough information. I mean, we can identify one of them occurs at +2. Let's see, is there any other things? I think in pre-cal we've talked about relative extrema in the past and maybe some absolute extrema. So what would we identify this point as? This would be, again, write these down, see if you get, like, pause the video, write what you think it is, and then push play and see if you got the same thing that I got. This is going to be a relative maximum. Even though it's not the highest maximum point for the whole curve, it is the highest point in the vicinity of the points immediately around it. So this is a relative maximum. This point right here would be a relative minimum. Okay, up here we would have a relative maximum again, back to a relative minimum, relative max, and then the endpoints. Actually there are no endpoints. So these things, it's implying that the graph goes on and on forever. So not only can we identify these as relative extrema, some of these we can also identify as absolute. Can you tell me which one would be your absolute maximum? Meaning it is the highest y value for the entire graph. If you said that x is equal to 0, that is correct. So this is not only a relative maximum, this is also the absolute maximum. Okay, can you identify where the absolute minimum would be for this graph? If you're struggling, that's because there's not one. The graph goes on and on forever to infinity on both the left and the right side, to negative infinity, I should say. So there is no there is no absolute minimum, which is completely possible. Sometimes you won't have either one. Okay, now I want you to think about what is happening at this relative maximum as opposed to this relative maximum. Earlier we said that we did not have a derivative at this one because there's a sharp turn. Would we have a derivative here, a derivative value? The answer to that question is yes. Your derivative value would be f prime of 0 is equal to 0 because you could make a horizontal tangent line here. Are there other places where we could make horizontal tangent lines? There are, I see at least 3 other places. You've got one here, here, and here. So notice where your relative extrema are occurring, you have a derivative of 0. That might come in handy later. Maybe I should write that down. Where I have relative. Now, again, is this true for all of them? Somebody should be raising a red flag and saying, no, it's not true at the cusp. So the cusp was not, this cusp was not differentiable. Therefore, there is no derivative value at this point. However, it's still a relative maximum. So that's interesting. A relative maximum happens when the derivative either does not exist or whenever you have a horizontal tangent line. I think I might want to write that down for later. We're going to go into that a little bit more, but those are just some thoughts that I had on this graph. We're going to be coming back to this graph quite a bit, so you might want to keep this handy. Okay, so let's keep going here. So let's say I have a function where I actually have the equation. Find the absolute maximums and minimums of f on the closed interval and state where these values occur. So I've got f of x is equal to 3x squared minus 24x minus 1, but I'm only looking at the interval from -1 to 5. So I have a closed interval and I'm looking at a quadratic function, so I want to find the absolute maximums and minimums. Now, if I wanted to, I could graph this function, you know, just look at it in a calculator, but we're too smart for that. Come on now, we're in AP calculus. We can handle this without a calculator. So let's think about on the last curve when we were looking at potential locations for maximums and minimums, that had a tendency to occur where my derivative didn't exist or where my derivative was equal to 0. So I'm going to start with that. So let's first, my first step here is I'm going to look for the locations of my horizontal tangents. And again, this is occurring when f prime of x is equal to 0. Okay, so I've got my function, so let's look at f prime of x is going to be 6x minus 24. I'm going to set that equal to 0. 6x minus 24. So at x equals 4, f prime of x is equal to 0. Okay, well, this gives me the x coordinate. I want to know what is the y coordinate at that location. So I need to find out what is f of 4. So I'm going to say 4 squared minus 24 times 4 minus 1. So I've got, let's see, 3 times 16, so 48 minus 96 minus 1. This is going to give me negative 49. So because at the point 4, negative 49, my derivative is equal to 0, okay, and my y value is equal to negative 49, this is what I like to call a possible candidate for an absolute minimum or maximum. I don't know what it is yet because I have to see what the rest of the graph looks like, but I'm going to call this one a candidate. Okay, so that's only where my horizontal tangents occur. I also want to look to see, are there any places where f prime of x does not exist? Okay, well, let's think about this curve. This is 3x squared minus 24x minus 1. Here we need to kind of go back to what we know about our parent functions. This is a quadratic parent function. What do we know about quadratics? They're continuous. They have either, in behavior, they both go to positive infinity, they both go to negative infinity. Yeah, but it's mainly a smooth curve. So for this one, even if I took the derivative, which we did a minute ago, it was 6x minus 24, that's a linear function. There is not a place where this function, this derivative function, does not exist. So there are no places, no x values where your derivative does not exist. So then our absolute extrema could occur here, or I need to see what's happening on my endpoint since I have a closed interval. Okay, so remember I'm looking at a graph that has, endpoints. Although I am guessing it looks like this, it might look like this. I know it's at least opening up because I have a positive leading coefficient, and it's an even. It's a parabola. I do know that. But I also, what if I'm looking at just this part of my graph? I have no idea. So let's see. What do our endpoints look like? So we're going to check endpoints. Okay, let me go down a little bit here. So the first endpoint was negative 1. So I need to check what is f of negative 1. So 3 times negative 1 squared. So 3 plus 24 minus 1, f of negative 1 is 26. Okay, so this is again what I call a candidate. Okay, well, I guess I should say the point negative 1, 26 is a candidate. And then I'm going to check my other endpoint, which was positive 5. So f of 5 is equal to 3 times 5 squared minus 24, 5 minus 1. So 3 times 25 is 75 minus 120 minus 1. That gives me f of 5 is equal to negative 46. So my other candidate is 5, negative 46. So there's kind of a lot going on here. So what I want to do here is I'm going to put this in a nice, pretty little table because I really only have 3 x values that I'm working with here. So step 4, when you're determining your actual minimum and maximum values, remember when we look at the minimums and maximums, this is the minimums and maximums of our y value. Those are our function values. So the minimum and maximum function values. So those could occur at the endpoints, which we had -1. We had a critical number. I say critical because that was where the derivative was equal to 0. Where was that at? Let me go back up here. I believe it was at 4. Yep, at 4. And then the other endpoint was at 5. At -1, our y value was 26. At 4, it was -49. And at 5, it was -46. So from here, we just look at the numbers that we have, and we determine the absolute minimums and maximums of our function in our interval. So the absolute minimum of f on the interval from -1 to 5, because remember, that could change if we looked at a different interval. So the absolute minimum of f on -1 to 5 is, looking at these numbers here, right here, -49, is -49. Okay? And actually I want to say, and occurs at 4, -49. Okay, so when they're asking specifically what is the absolute minimum or maximum, they are just looking for this value right here. I like to go a little extra and tell them that it also occurs at 4, -49, so we know where the x value is that this is located. But specifically, if they just wanted the absolute minimum or maximum, technically you only need this piece right here. So then the absolute maximum of f on -1 to 5, looking back at my chart yet again, oh, winner, it's 26, is 26, and occurs at -1, 26. Okay, so that is how we find the absolute minimums and maximums. Just a quick recap. We started out by finding the horizontal tangents, because that's going to tell us where I have a curve or a turn in my function. It's going to either change directions, or maybe it won't change directions, but probably there's a good chance that it would, especially since I'm looking at a quadratic. So I looked for where my horizontal tangents were. Then I looked to see if I had any sharp turns or cusps, which I didn't because my function was a quadratic. Its derivative is linear. Linear functions are continuous over the entire real line, so we're good there. And then I plugged in my endpoints to see what those y values were, 26 and -46. Then I put those into my fancy chart here, and then I just determined what my absolutes, minimums, and maximums were from there. Okay? Hope that made sense. If not, go back a minute and watch it again. It's great times. So let's come up with a definition here for these extrema. Maybe. I thought I clicked the next page. Maybe not. Uh-oh. There we go. Okay, so the definition of extrema. So let f be defined on an interval I containing c. I, we've talked about this before, that's just some interval that they specify. On the last function, it was from -1 to 5. And then c is some x value that we don't know what it is yet. Okay? So if f of c is the minimum of f on I, f of c is the minimum of f on I if f of c is less than or equal to f of x for all x in I. Basically, it is the smallest y value over the entire interval. The flip side, f of c is the maximum of f on I if f of c is greater than or equal to f of x for all x in I. It is the highest y value over the entire interval. Okay? And then the minimum and maximum of a function on an interval are the extreme values, or extrema. Extrema is just the plural way of saying extreme values. Those are the same thing. So the minimum and maximum of a function on an interval are the extreme values or extrema of the function on the interval. The minimum and maximum of a function on an interval are also called the absolute minimum and absolute maximum, or global min and global max on the interval. Most of the time, I would say that we stick with absolute min and max, but you will hear people say from time to time global min and max, because over the entire function, they want to know what is the global maximum or global minimum. Things like that. Just another synonym for you guys. Okay, so I want you to pause the video right here, follow the same procedures that we did on the last function, and see if you can identify the absolute minimums and maximums of this function. Okay, start with step 1, finding your horizontal tangents. Follow all the steps. I'm going to go ahead and put them on here as well. I'll walk you through it, but I want you to see if you can try it first on your own and then check to see if you get the same thing that I do. Okay, so again, pause the video. Did you do that? Okay, welcome back. So step 1, let's check for a horizontal tangents. Okay, so f prime of x. So 18x squared minus 24x cubed, and then plus 5, that just goes away because it's a constant. So then I want to set that equal to 0. So 0 is equal to 18x squared minus 24x cubed. I can factor some of this stuff out here. I'm going to factor out, let's see, a 6x squared. So I'm left with 3 minus 4x. So that means x is equal to 0. And if I set this one equal to 0, I would get 3/4. Okay, so this is where I have a horizontal tangent, where my graph is potentially turning. But I need to find my y values at these points. So let's see, f of 0. That one's nice. That's just going to be 5. Super easy to plug in. F of 3/4. Remember, fractions are what, guys? You guys know what I always say. Well, hopefully, I think I've said it by now. Fractions are friends, not food. Don't put this in your calculator. Come on now. It's not that bad. We're going to say 6 times 3/4 cubed minus 6 times 3/4 to the 4 plus 5. So that's going to be 6 times, let's see, that's going to be 27 over 64 minus 6 times 81 over 256. Totally did that math in my head. I know, I'm awesome. All of that adds up to be 721 over 128. Mervin, those math skills are on point. I know. Both of these, though, are our candidates for potential absolute min and max. Okay, now, step 2, where is my derivative non-existent? F prime of x does not exist at, let's see, my derivative is a cubic function. We know that cubic functions inherently are continuous. They do have odd end behavior. That's okay. That's fine. But they're continuous. So there's not a place where my derivative would not exist. So there are no candidates that came from that particular area. All right. Let's check our endpoints here. Oops. Okay, so checking our endpoints, we're going to have f of -1, 6 -1 cubed minus 6 -1 to the 4th plus 5. So -6 minus 6 plus 5 is -7. F of 2 is going to be 6 times 2 cubed minus 6 times 2 to the 4th plus 5, 6 times 8 minus 6 times 16 plus 5, 48 minus 96 plus 5, -43. So I have a candidate here, a candidate here, here, and here. 4 possible candidates for our absolute extrema. To make sure I collect them all together, I'm going to put them in my nice little table here to determine so x, f of x, I started out at -1, but I also had 0, 3/4, and 2. At -1, my y value was -7. At 0, it was 5. This is 721 or 128. And then this is -43. So just by looking at this, what is the absolute minimum? Ding, 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 right here. So the absolute minimum of f on -1 to 2 is -43 and occurs at 2, -43. The absolute maximum of f on -1 to 2 is, let's see, I know it's automatically not that one, so between these last three, well, no, it's either between these two. I can pretty much determine that 128 will go into 721 probably more than 5 times. So I'm going to say that the absolute maximum is 721, 128, and occurs at 3/4, 721, 128. Boom, done. Okay, hopefully you got the same thing. If not, check your math, see what you did wrong. Hopefully maybe just a little minor thing that you can easily fix. Okay, so we've talked about absolute extrema. Let's switch gears a second and talk about what is the definition of a relative extrema, because all we've done so far is looked at our absolutes. What is the absolute highest point of our graph? What is the absolute lowest point of our graph? But what if we wanted to know where the relative extrema occur? Because think back to that very first function we had. This guy right here. I didn't have an absolute minimum, but I did have several, or at least 2 relative minimums. So what if I wanted to find out what those values were? Well, luckily some of the same concepts occur, but let's talk about the definition. So if there's an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum of f. Or you can say that f has a relative maximum at C, f of C. So notice here, now we're specifically talking about open interval. Everything we've done on the last 2 problems was talking about a closed interval. That's very important. If there is an open interval containing C in which f of C is a minimum, then f of C is called a relative minimum of f, or you can say that f has a relative minimum at C, f of C, okay? Again, it's not saying what is the relative minimum value. Before we could say what is the absolute minimum or absolute maximum value, because there's only one possible absolute max or absolute min. However, there's not, I mean, there could be one relative maximum or one relative minimum, but then you would, you wouldn't specify that f has a relative minimum of blah. We just don't say that. Instead, we just talk about where it's located. So we talk about it's located at C, f of C. Also, relative maximum minimum are sometimes called local maximum minimum instead of global, like we had for our absolute extrema. Okay, so let's make sure we understand the difference between these two. So looking at this graph right here, from it looks like -2 to +4, f has an absolute maximum at, since it's asking at, we want to know what is the point that is located. That point is 4, 21. That is the location of the absolute maximum. The actual absolute maximum value is 21, but it occurs at 4, 21. The absolute minimum occurs at -2, -15. F has a relative maximum at 0, 5, and a relative minimum at 2, 1. Okay, now notice I didn't specify that these could also be relative, because relatives can only occur on open intervals. Okay, so now granted this has a closed interval. I get what some of you are maybe raising your eyebrows for, but if I were to look at just a random open interval around this point, 0, 5 is the location of my relative maximum. A random open interval around this point right here, 2, 1 would be my relative minimum. But the 2 points on the ends, I can't compare them. Basically, I can't compare points on the left and the right side because there's only one side. So because of that, this can't be a relative. This could only be an absolute. Same thing here. This could only be an absolute. It could not be a relative because I can't compare both sides. But see how at this point I have two sides to look at? Same thing here. I have two sides that I can look at. So I can say in relative to points on either side, it's the maximum or a minimum. Okay, let's look at some more examples here. Maybe. Here we go. So I want you to name the maximum and minimum points if possible. Again, this is a good opportunity for you to pause the video, fill in your answers, and then check it with what I have when you come back. So for part A, we have a minimum at 0, 1. Now notice, did they specify absolute or local? No. If they don't specify, it's understood that they want the absolute minimum value of the function or the absolute maximum value. If we wanted relative, we would be much more specific. But if we just say minimum, we are technically talking about the global or the absolutes. So this function, the absolute maximum, would be at the point 2, 5. Okay. For part B, the minimum is going to be, or example B, is at 0, 1. Where's the maximum? Well, this curve looks a lot like this curve over here, but notice this curve has an open circle right here. So that means this point technically does not exist on my function. I get infinitely close to it. I could take the limit as x approaches 2 from the left, but I'll never actually get to this y value right here. So because there's not a specific y value, there's technically not a maximum value. There's a limit. Okay, we can take the limit, but since we never actually get to a specific y value, because for every value you get to, there's always one a tiny step closer, a tiny step closer, and a tiny step closer, there's actually not a maximum value. Okay? And you'll notice something very similar on example C. The minimum, notice we have another open circle. Yes, the limit exists. However, the function itself does not exist here. So there is no minimum value. Okay, but there is still a maximum at 2, 5. So what do you notice that's happening on A that does not occur on B or C? What's happening is that this is a continuous function on a closed interval. This is a continuous function on an open interval. This is a non-continuous function. Okay, there's an open interval here and then an open interval on this side, or partially open. Okay, so in order for you to have both an absolute minimum and maximum, two things have to occur. Your function must be continuous on a closed interval. Okay, this goes into our next value theorem. We've had a couple others in the past. This is what we call the extreme value theorem. If f is continuous on a closed interval, a to b, then f attains an absolute maximum value, f of c, or an absolute minimum value, f of d, for some numbers c and d within a and b. Now, a and b could be the same thing as c and d, because we know that we could have absolute minimums and maximums on our endpoints, but they don't have to be. What this theorem is stating that as long as your function is both continuous, both continuous and on a closed interval, then you have to have an absolute maximum and an absolute minimum value. Okay, what other function, what other value theorem had the same two conditions? Does anybody remember? That was our first one, EVT, the intermediate value theorem. Its conditions were it had to be continuous on a closed interval. Okay, and then we also had another one, MVT. Now, it didn't have to be, well, it did have to be continuous on a closed. That was the first step, but it had an extra one. What's the extra condition for this one? Continuous on a closed. It also had to be differentiable on an open interval. Okay, at some points in between the curve, between the endpoints, you had to be differentiable as well. So these are the three value theorems that we've talked about so far. You're definitely going to want to make sure you memorize. You've already gotten these two memorized from before. Make sure you now memorize this one in your repertoire of value theorems. So we've got intermediate value theorem, mean value theorem, and now the extreme value theorem. Okay, so this comes in handy whenever we want to talk about critical numbers and critical points. So now we've kind of already talked about these a little bit. I haven't specified the official name of these. So this is just some vocab that's kind of pulling everything we've done today together. So a critical number and a critical point. A critical number, let f be defined at c. If f prime of c is equal to 0, or f is not differentiable at c, then c is a critical number of f, and the point c, f of c, is a critical point of f. Why are these two things so critical? Pun intended. Right here, when this happens, think about it. F prime of c is equal to 0. You have a horizontal tangent. Okay, that's where your function could change directions possibly. Or if f is not differentiable, that's when we have a sharp turn or a corner or a cusp. So that could be where our another location where we have a relative extrema or an absolute extrema. Okay, so speaking of, we have a theorem that specifies relative extrema only occur at critical numbers, and critical numbers are only the places where f prime of c is equal to 0 or f is not differentiable. Okay, so the converse of this statement. Ooh, do you guys remember the word converse? Think back to geometry. Anyone? It's been a little while. I'm not talking about the brand of shoes, by the way. I'm talking about when you reverse the statement. So if your theorem is that relative extrema occur only at critical numbers, the converse is that critical numbers are all relative extrema. What do you think? True or false? I know this one has to be true. Okay, we've already talked about that one. What about this? Critical numbers are all relative extrema. True or false? Well, some of you know my style enough to be like, well, Murphy wouldn't ask this question if it probably wasn't false. You are correct. It is false. But anytime we have a statement that we have to prove is false, we must provide a counterexample to justify. So one function, that's a great counterexample, is x cubed. F of x equals x cubed. If I were to take the derivative, f prime of x is equal to 3x squared. So I'd have a critical number at x equals 0, because at 0, x is equal to 0, and I have a horizontal tangent right here. However, is this point right here a relative min or max? No, not for this one, because my function is always increasing. It's because my function is always increasing. Yes, this is a critical number. This is a critical point, but, or x equals 0 is a critical number. This point 0, 0 is a critical point. However, it is not a relative minimum or maximum. Okay? And then let's think of, ooh, here's another good function. The cubic root of something. So f of x equals the cube root of x. Again, my function is always increasing and it's continuous, but if I were to take the derivative of this, so this is f of x equals x to the 1/3, so f prime of x would be 1/3 x to the negative 2/3. So because your derivative is 1/3 x to the 2/3, my derivative does not exist at x equals 0. On my derivative function, I would have a sharp turn at 0. So because my function is not differentiable there, okay, that would be a critical number at 0, but it would not be a relative extrema because my function is always my function is always increasing. Okay, I hope that makes sense. If not, go back and watch it again. Maybe it'll make more sense the second time. Let's do some quick guidelines for finding extrema on a closed interval. Oh wait, you technically have already done this. The thing we did on our first two examples, I didn't actually tell you this, but this is what I like to call the candidates test. We've already done it. It's just that now we're going to kind of put it all into words as to what you did here. So to find the extrema of a continuous function on a closed interval, use the following steps. First step. Number one, find f prime of x and the critical numbers of f in AB. We did that by finding the horizontal tangents first, and then we found where f prime of x did not exist. Sometimes that happened, sometimes it didn't. And that's going to be the same thing where f prime of x is equal to 0. Sometimes it happens, sometimes it doesn't. But either way, those will give you your critical numbers. Evaluate f at each critical number. Plug those into your original function and find out what your y values are. Evaluate f at each endpoint. I feel like that's pretty straightforward, but yeah, okay. Number 4, the least of these values is the minimum, the greatest is the maximum. This is where I created my table in set 4. You know, you make the table and you plug in the points, but basically the highest is the maximum, the lowest is the minimum. That's candidates test in a nutshell, okay? And technically, you have already done that. So because we have already done that before, here's what I want you to do, okay? I want you to apply said test to this example, okay? I want you to pause the video, apply it to this example, and see if you get the same thing that I got. I'm actually not going to work this whole thing out. I'm going to go ahead, I'm going to work it out, but I'm not going to talk you through this one. Oh, I guess maybe I should. You have a 2/3 up there. That might cause some hiccups. All right, I'll go ahead and work it out. But I still suggest that you try it on your own first, and then come back and see how your answer compares to mine. Okay, so step 1, I need to find critical numbers. And to do that, I'm going to set f prime of x equal to 0. So f prime of x is going to be 2x to negative 1/3 minus 2. Set that equal to 0. So 0 equals, I'm going to clean this up a little bit here, 2 over cube root of x minus 2. So bring that over. I'm going to cross multiply and divide here. And so basically, cross multiply, divide, you get the cube root of x is equal to 1. Multiply by 2, divide by 2. 2 over 2 is 1, guys. Right? So cube both sides. X is equal to 1. This is a critical number, because this is where my derivative is equal to 0. Okay? I need to figure out if I have any places where, so this was where f of x was equal to, f prime of x was equal to 0. Is anywhere where f prime of x undefined? What do you guys think? This is f prime of x. Is there anywhere where I can't plug in an x value? X equals 0. If I plug in a 0 into my derivative right here, okay, I would have a 0 in the denominator, which we are not allowed to have. So because you have a 0 in the denominator, my derivative does not exist at x equals 0. This is another critical number. So I have 2 critical numbers so far. X equals 1, x equals 0. Step 2 tells us to evaluate our function at those 2 critical numbers. Because I have some space, I'm going to just do that right here. So f of 1 is going to be 3 times 1, so 2/3 minus 2 times 1 plus 1, which is 2. And then f of, let's see, my other one was 0, is going to be 3 times 0, so the 2/3 minus 2 times 0 plus 1. That's a 0 right there. And you get 1. Okay? So then, this right here, remember we called this a candidate. Right? This is a candidate for an absolute min or an absolute max. This is another candidate. I don't know which one it is, but this is a candidate. If I were to combine this and talk about the point 1, 2, or the point 0, 1, okay, these are both critical points, okay, because these are the points at our critical numbers, right? Step 3, we needed to evaluate our endpoints. So we're going to look at f of negative 1 and f of 8. So 3 times negative 1 to the 2/3 minus 2, negative 1 plus 1. That works out to be 6 f of 8. So 3 times 8 to the 2/3 minus 2 times 8 plus 1. Got to do a little bit more math here. That's going to be cube root of 8 is 2, squared is 4, times 3 is 12, minus 16 plus 1. I get negative 3. So I'm going to put all of this into my chart for step 4. And I've got x, f of x. Let's see, I had negative 1. My critical numbers were 0, 1. My other endpoint was 8. At negative 1, my y value was 6. At 0, my y value was 1. At 1, it was 2. And at 8, my y value was negative 3. So my absolute minimum of f on the interval from negative 1 to 8 is, my absolute minimum value is going to be this negative 3. So is negative 3 and occurs at 8 comma negative 3. The absolute maximum of f on negative 1 to 8 is, well, the highest is going to be 6 here. So is 6, and I was trying to clean that up. That made it worse. Occurs at negative 1, 6. So here, the absolute extrema still occurred on our endpoints. That doesn't always happen. It could. It doesn't have to. But what I would recommend that you do here to confirm your math here is go ahead and plug this into your calculator. Plug the function in. See if it matches up with what you've got. I want you to be able to do this math on your own without checking the calculator. But I want you to recognize that you can still check your work afterwards, especially since you are learning this from a video. Okay, I've got one more example. Should be kind of short. Again, pause the video. Try it on your own. Push play. Make sure you got the same thing. If you got something different, watch how I work through it. See where you went wrong. Maybe it was just a simple math mistake. Who knows? Okay. Okay, so again, we're finding absolute minimums and maximums. So step 1, find critical numbers. Okay, so critical numbers. All right, so I need to do that by first taking my derivative. So f prime of x. Ooh, we get to use some fun. Oh, this is a trig one, guys. We could use some fun trig derivatives. I know you've been missing those because we've just done some polynomials today. And now we're back to the fun stuff. All right, so, ooh, what rule do I have to apply here? Anyone remember? That's right, the chain rule. Bring the 2 out, so 2 sine of x times the derivative of sine, which is cosine of x, plus the derivative of cosine. Oops, I don't need a plus. I need a minus. Derivative of cosine is negative sine of x. That is my derivative. Okay. I'm going to set that equal to 0. So 2 sine x cosine x minus sine x. I'm going to factor out sine of x here. So sine of x to cosine x minus 1. Where is sine of x equal to 0? Where is cosine of x equal to 1/2? Well, that's going to be, let's see, this occurs when x is equal to 0, pi, actually any multiple of pi. However, my interval only goes from 0 to 2 pi, so I don't want to write all of that multiples of pi. I just want to write the ones within the interval I have. So 0, pi, and 2 pi. Again, cosine of x is equal to 1/2. There are infinite answers to this equation, but I only want the ones that satisfy this interval, so basically within the unit circle. And that's going to occur when x is equal to, let's see, pi over 3 and 5 pi over 3. So these are all of our critical numbers. Now, luckily, you might notice your critical numbers, 2 of them are also your endpoints. Okay, so when I go to evaluate them, I'm going to have them all already evaluated. Excellent. We need to check, where is f prime of x does not exist or non-existent? Let's think about this. Is there any value that I can't plug in to sine, cosine, or sine? No. Each one of these, if I can't tell what the function looks like as a whole, I look at individual pieces of it. Is there anything that I can't plug in here? No. Sine is continuous over the whole real line. Cosine is continuous over the whole real line. So just their multiple is also continuous over the entire real line. Same thing with sine over here. So because there's not a value of x that I cannot plug in here, there is no places where my derivative does not exist. Okay? So then I can really go straight into evaluating my critical numbers. So I'm going to kind of abbreviate this here. Go ahead and straight into my table. I think that's like step 4, but x, f of x. Let's see. So I have 0. I want to make sure I go in numerical order here. So 0, pi over 3, pi, 5 pi over 3, and 2 pi. Okay. F of 0, sine squared of 0, or sine of 0 is 0, plus cosine of 0 is 1. Let's see, pi over 3. So you're going to have sine of pi over 3. Sine of pi over 3 is root 3 over 2 squared. So root 3 over 2 squared plus cosine of pi over 3, we know is 1/2. So that's going to be 3 over 4 plus 1/2. So 3/4 plus 2/4, so 5/4. Sine of pi is 0. Cosine of pi is -1. So this is going to be -1. 5 pi over 3, this is just negative root 3 over 2 squared plus 1/2. So it's 5/4. And then if I plug in 2 pi, sine of 2 pi is 0, plus cosine, which is 1, so 1. Okay, so find the absolute maximums and minimums. Now, what do you notice here? Let's see, the absolute, actually the absolute minimum only occurs in one spot, right here. But I have 2 locations of the absolute maximum. Now, I still only have one absolute maximum value, but it occurs at 2 places. This is possible, and it's perfectly fine. Okay, so we'll say the absolute minimum of f on 0 to 2 pi is, we said, was -1 and occurs at pi comma -1. The absolute maximum of f on 0 to 2 pi is 5/4 and occurs at both places, pi over 3, 5 over 4, and 5 pi over 3. That's a 3. Okay, maybe not. 5 pi over 3, 5/4. Okay, again, you only have one absolute max or one absolute minimum value. Okay, but it can occur in multiple locations, which is exactly what is happening here. Okay, so yeah, that's pretty much it for that one. Let's see what else we have here. I think that's it. Oh, yeah. Yeah, so the homework that goes with this worksheet, or the homework that goes with these notes, is called 3.1 worksheet EVT and candidate test. That is posted in Canvas. If you have questions on this stuff, Khan Academy has another great video. You can check your book, although I think a lot of the examples might be the same. But yeah, Khan Academy is good. And then also Prof. Rob Bob. Make sure you check with him, see if he's got any more stuff on extreme value theorem and candidate test if you are still confused.